Hey everyone, and welcome. So, you know how every function in math kind of has its own secret rulebook? A set of rules that decides what it accepts and what it can spit out? Well, today, we're going to crack that code. Think of us as function detectives. By the end of this, you'll be able to look at any function and figure out its hidden story.
All right, let's jump right in with a little puzzle. And don't worry about any complicated formulas for now. Just use your gut. A dog is tied up for less than 3 minutes. So think about it. What are some possible numbers for how long he was tied up in seconds? And what about the number of times he could have barked? Are the rules for time and barks going to be the same? Let's find out. So this whole dog scenario, it's not just a cute puzzle. It's actually the key to unlocking a really big idea in math. Let's break down the clues, shall we?
Okay, so what's super interesting here is how we've split up our two variables, time and barks. Let's look at time, our input. Could it be 15 seconds? Yeah, totally. 84.5 seconds? Sure, that works. But what about 300 seconds? No way, right? The problem specifically said less than 3 minutes, and that's 180 seconds. So 300 is out. Now, let's switch over to the barks, our output. 15 barks? Makes sense. But 84.5 barks? How does a dog do half a bark? It's just not a thing. So that's impossible. What about 300 barks? I mean, that's a very noisy dog, but yeah, it's technically possible in under 3 minutes. And just like that, we found the hidden rules. So for our input, time, pretty much any number between 0 and 180 works, even decimals. But for our output, the barks, it's a totally different story. It has to be a whole number. You just can't have part of a bark. And that's the big takeaway here. The rules for what you can put in aren't always the same as the rules for what you can get out. Okay, so we found these hidden rules, but what are they actually called? Mathematicians, of course, have official names for this stuff. And once you know them, you've pretty much cracked the code. First up, we've got the domain. This is just the fancy name for this set of all possible inputs. So for our dog puzzle, the domain was any number of seconds bigger than 0, but less than 180. It's basically the list of ingredients the function is allowed to use. And the outputs? Well, that's called the range. The range is the complete set of everything the function can possibly spit out. For our barking dog, the range was all the whole numbers, 0 barks, 1 bark, 2 barks, and so on. You know, here's a really easy way to remember this. Think of a function like a vending machine. The domain is what you're allowed to put in it, right? It might only accept quarters or dollar bills. You can't stick a pebble in there. The range is everything it can possibly give you back. Soda, chips, candy, whatever's inside. You can't put in a rock, and you're definitely not going to get a puppy out of it. The machine has its rules. Okay, so we've got the lingo down. Domain is the input, range is the output. Now, let's take these detective skills and apply them to a new piece of evidence, a graph. Graphs are awesome because they literally paint a picture of the function's entire story. All right, check out this graph. That curvy line you see? That represents every single input and output pair for this function. So your mission now is to figure out the domain and the range just by looking at this picture. Basically, where does this graph live? So to find the domain, all you have to do is look at the x-axis, the horizontal one. We're going to scan it from left to right. So how far left does our graph go? Looks like it starts at an x value of -4. And how far right does it go? All the way to +4. That means our domain is everything from -4 to +4, including those endpoints. All right, now for the range, we're going to do the exact same thing, but this time we're scanning up and down on the y-axis. So what's the absolute lowest point this graph hits? That's down at a y value of -1. That's our minimum. And what's the highest point, the very peak? That's up at a y value of 3. That's our maximum. So the range is simply every number between that minimum of -1 and that maximum of 3. See, the graph just lays it all out for you. And yeah, just to really lock that in, the highest point, the absolute maximum value this function can spit out is 3. And on the flip side, the lowest point it ever reaches, the minimum, is -1. And those two numbers, the max and the min, they set the boundaries for our entire range. Okay, but this isn't just some abstract math puzzle. Understanding the domain is absolutely crucial when we start using functions to describe things in the real world. Because let's be real, in the real world, not every number makes sense. The context of the problem adds a whole new layer of rules we have to follow. So before we jump into our next couple of real-world cases, let's do a super quick review of our number types. This is important. You've got your whole numbers, that's just 0, 1, 2, 3, your basic counting numbers. Then you've got integers, which is all the whole numbers plus all their negatives. And finally, rational numbers, which is basically any number you can write as a fraction. That includes decimals that stop or repeat. Knowing which one to pick is the whole game.
All right, detective, case file number 2. We've got a function that's modeling traffic, and the input n is the number of vehicles on the road. Take a look at these 4 options. Which set of numbers actually makes sense if you're counting cars?
And the answer has to be number 4, because context is everything here. Think about it. Can you have half a car driving down the road? Or -2 cars? Of course not. The only numbers that make any sense at all are the whole numbers. 0 cars, 1 car, 2 cars, and so on. So option 4 is our only logical choice. The real-world problem totally defines our domain.
Okay, last case file for today. This graph is showing us a rocket's flight, its height over time. Our input here is t, for time. The question is, what is the domain? What's the complete chunk of time that this graph is describing? And hey, pay close attention to those little brackets and parentheses in the answers. They matter. The answer is option 2. If you look at the graph, the rocket takes off at time 0, and it comes back down and hits the ground at the 4-second mark. So the function is only describing what happens during that interval, and those square brackets are key. They mean that both 0 seconds and 4 seconds are included in the domain, which makes perfect sense, right? That's the launch and the landing.
So as you can see, domain and range aren't just random rules from a textbook. They're like the guardrails that make sure our math actually lines up with reality. It doesn't matter if you're coding a video game, building a financial model, or, launching a rocket. Domain and range define the boundaries of what's even possible. So every function really does tell a story. And now that you know how to read its rules, what stories are you going to uncover?